Ты ради себя.
Yes. And that said,
So tonight, again, my name is Alan Wolke. I'm W2aew.
Yes.
I'm in Central
And that
New
said,
Jersey.
I will be. Yes. And that mute. Good evening, everyone. That said, well, hello. Mute.
Again, a little introduction to the Nano VNA. Again, I'm the technical coordinator for the Northern New Jersey section, and I've got a little YouTube channel here we can talk about later. So what we want to do, why do we want to talk about this? Mainly because these ridiculously inexpensive Nano VNAs have hit the market, and it's something that typically VNAs were outside the realm of the possibility for most hobbyists because of the price. But now that they're so inexpensive, we all can go play with them. So the first thing we want to do is talk about what a vector network analyzer is, because it's something that again, most of us haven't used, and you want to understand what it is. But you've probably used an antenna analyzer of some sort, and so you've actually used something that's similar to a vector network analyzer, but you didn't know it. So the second thing we'll talk about is what a VNA is good for, and why do we care about it, and then we'll take a look at the Nano VNA specifically. So first, what is a VNA? VNA stands for Vector Network Analyzer, and if you did a Google search for a definition, you might find something like an instrument that measures the magnitude and phase of the reflection and transmission properties of the ports of a device versus frequency. And you might say, well, what the heck is that? It doesn't really help me understand what a VNA is. So let's break it down and try to make it a bit more understandable. So first, let's take a look at what VNAs look like. Here's a couple of examples of commercially available VNAs. These two first examples are relatively low-cost professional VNAs from Tektronix and from Copper Mountain, and then a high-end VNA from Keysight. And again, it's typically an instrument that's used to characterize RF devices. And they used to only be used by RF engineers in a professional environment, primarily due to cost. These two instruments up on top here are, $8,000 to $12,000 instruments, and those are low-cost VNAs. Professional units can cost many thousands or more. This 4-port device from Keysight is only $238,000. Okay, so as you can see, most of us as hobbyists wouldn't have access to these things. Now, there's a lot of acronyms and terminology kind of associated with VNAs. So if you were going to go look online to research how to use it, you're going to see some of these things. So we're going to clear up some of that terminology and alphabet soup here first. So the first is DUT. What does DUT stand for? DUT is simply the device under test. It could be an antenna, it could be a hunk of coax, it could be a filter, it could be an amplifier, etc. That's what the DUT is whatever it is that you're testing. Any DUT or any device you're testing is going to affect the signal going through it in one way, shape, or form. Okay, the input impedance is going to affect the applied signal, and of course, the device itself, if it is a 2-port device, is going to affect the signal going through it and passing through it in some way. Okay, and especially when we talk about things like transmitters and antennas, we want to talk about maximum power transfer, and most of us have learned that in order to get maximum power transfer from any kind of a source into any kind of a load, is you want the source and load impedances to match. Well, we say resistances match, but the reality is you want the complex conjugate impedances to match. Now, I'm not going to talk a whole lot about this, but I just want to kind of bring up the term, and this is part of why RF engineers care about these things. But for our use, we don't really have to care about this too much, unless we want to design things like matching networks for an antenna system, for example. And we could talk a little bit about that later. So when it comes to RF signals, it helps to think of signals as waves. And rather than think of them as just a voltage and a current, we think of them as a wave with a magnitude and a phase. Okay, we can see these two waves up here have slightly different magnitudes and a slightly different phase. And one way to think about phase, because phase can confuse a lot of people, phase is just a delay. Is one way to think about it, right? These two sine waves that I show here and here differ in phase by about 90 degrees, but it really is, you can see it's just a time shift. So that's another way to think about phase. This little moving graphic here is illustrating what happens, for example, if I had a signal reflecting off of a load, and maybe that magically making this transmission line longer between my source and my load, we can see how the reflected wave, which is the red wave, is varying in phase with respect to the incident wave because of the distance between the source and the load. So these are some reasons why we want to think about phase, because propagation delay down a hunk of coax and things like that is going to affect the phase of the signal that's seen at the other end with respect to the phase that was applied. So again, when we start thinking about waves and a VNA, one of the things what we're going to be concerned ourselves with is we're going to have a signal that's being applied from the source, and then some of that signal, ideally, if we have a two-port device, is going to go through that device. It could be an amplifier, could be a filter, could be a mixer, whatever it might be. And those are what are called the transmission properties of the DUT. And also, if we have an impedance mismatch at this point here, we may have some signal reflected off of that input port to the device. Okay, and those we call, obviously, the reflection properties. So the DUT reflection and transmission will alter both the magnitude and phase of the signal that's being applied. And that's what we look at on a VNA. Okay, so let's take a look at that a little bit closer. So this is what a basic VNA looks like inside, and this is similar to what is inside, say, the Nano VNA. We've got an RF source over here that's going to be applying a signal that ultimately is being applied to an input port of a device, and then the output port's going back in. Output is going back into another port on the VNA. We have a set of directional couplers or bridges inside the VNA that essentially detect the signal that's being applied and being measured here. And then also, if any signal that's reflected off of the input port that comes back, that signal is essentially picked up and measured by a separate receiver. So the directional couplers will pick up the signal and give you samples of the signal that are going in either direction. So we can see the incident signal and the reflected signal. And of course, if we've got a multi-port device, we'll measure through that. So inside the VNA, there's effectively 3 receivers. Those receivers are going to be used to measure the incident signal. We'll call it the reference receiver. That's where the R comes from. And then we've got the reflected signal off of port 1. We'll call that the A receiver. And then the signal that comes through the DUT is measured by the B receiver. So these receivers measure both the magnitude and phase of the incident, reflected, and transmitted signals through our device under test. All those results from those receivers are then computed into the various displays that a VNA can show you. So the measurements that are made off of port number 2, okay, are the transmission properties. And they're based on the ratio of the signal measured with this B receiver compared to the signal measured by the R, the reference receiver, right? So it's B over R. So that is really a measure of the gain or loss of the DUT. Another way to look at that is something called S21, and we'll talk about what that is here in a moment. It can also be called the transmission coefficient of the DUT. And then you can also measure things like the insertion phase or group delay of that device under test. How much of a delay you have going through it, and how does that delay change versus frequency? There's ways of characterizing that. And these are all the transmission properties you can measure by looking at the ratio of B to R. And obviously at port 1, if we've got signals that are being reflected off of the input and coming back, now we can make reflection-based measurements based on the ratio of what's measured in the A receiver compared to R. Okay, so that's our A over R term here. And this is some familiar things like VSWR or reflection coefficient, or sometimes also called S11, or return loss, which is really just it's just the inverse, if you will, or opposite sign of reflection coefficient. And we could also measure things like the input impedance looking into that device, because by knowing how much signal we have reflected back and at what phase it's being reflected back, we can compute what that input impedance looks like. So this is basically what a vector network analyzer does. So it can measure both these transmission and reflection properties of our DUT. Now, most professional VNAs will also have a source and couplers on both ports. So that's called a 2-port, 2-path VNA. The little Nano VNA that we're talking about today does not have a source and couplers on the second port. So this is called a two-port one path. So it's got two ports, we've got one transmission path and one reflection path measurement. Okay, so it's called a two-port one path. So what's a VNA good for? So for just making measurements using a single port, we're making reflection measurements. Again, SWR of an antenna versus frequency, measuring complex impedance of maybe a filter or an antenna system, looking at components, resistors, inductors, capacitors, things like that. We also, through some additional processing, can actually compute the length of a feed line, or therefore even a distance to fault, to say, hey, maybe I got a coax run going up a tower and all of a sudden things don't work right. You can actually use a VNA with some additional processing in the VNA to actually compute the distance to maybe an open or a short in that coax or a bad connector or something like that. So you know how far you got to climb up the tower. Okay. So if you make measurements using both ports, both the source port and the transmission measurement port, you can essentially measure the transmission properties of the device. And this could be looking at the filter shape or loss through a filter, looking at loss in a feed line versus frequency, maybe the delay through some device under test, looking at like an amplifier gain and frequency response if you take some care with attenuation and things like that. So these are some of the things you can do with transmission measurements. So obviously this means that we can use a VNA to characterize everything from antennas to duplexers to filters, inductors, caps, splitters, balance, chokes, phasing networks, etc. All of these are different types of devices and different things that we can measure with a VNA. And you may recognize that some of these things are things that you can measure with an antenna analyzer and things like that. So, and that's where, most hams, if they're going to pick up a VNA, are going to be essentially using it as a glorified antenna analyzer. And that's fine, because even though this can do a lot more than an antenna analyzer does, these little nano VNAs are less expensive than a lot of the antenna analyzers that are out there. So not a bad way to go. So we mentioned a little bit earlier these S11 and S21. These are called S parameters. And this is something that confuses a lot of people, because unless you kind of live in the RF design world, you probably don't know what S parameters are. And they sound kind of foreign, and it's like they're scary. So what do they mean? Okay, what is it? So let's break that down, make this nice and easy for you. The S parameters stand for scattering parameters. Now I know that doesn't help you either. Okay, it has to do with the way the math is structured, but let's break it down, make it real easy. It's really simply a ratio of a measured response, okay, the response measured on port X in response to a stimulus that's being applied from port Y. Okay, so on a VNA, this typically, port 1 is the port typically labeled port 1 and port 2. So if we said we want to look at, let's say this is what I said here. So the response at port X from a stimulus applied from port Y. So for example, S11 is the ratio of the reflected signal A measured on port 1 in response to the signal being applied from port 1. So that's S11. So in a sense, it's really just that reflection measurement, and it's the ratio of the reflected signal to the applied signal. Very simple. Okay, it winds up being a complex number because we characterize it both in magnitude and phase, so we know how much phase shift the device is imparting on that reflected signal. Okay, so that's really just the reflection at the DUT port. S21 is going to be the response measured at port 2 in response to the signal applied by port 1. So that's where the S21 comes from. So again, it's the signal measured in that B receiver compared to what's measured in that reference receiver. Okay, where R is again the applied signal reference. So we looked at the R, A and B receivers. This is essentially that ratio. So that's really all those two things are: is the reflection at the ports, the DUT's input port, and the response through that DUT from one port to the next. And that's really all the S parameters are. So they're really not very scary at all. Okay. So, so when someone says to you S21, they're talking about the insertion loss or gain of a device. They talk about S11, they're talking about the reflection properties very akin to and very mathematically related to SWR. Okay. So another thing that becomes confusing with VNAs is something called a user calibration. And that's something that you've got to do with a VNA. We're going to talk about why here. Because I say, well, I can pick up my antenna analyzer, I just use it and it works. Why can't I do the same thing with a VNA? Well, part of the reason, there's a couple of different reasons for that. So let's go take a look at that. So why do we need to run what's called a user calibration on the instrument? Okay, isn't it calibrated from the factory after they build it? Well, there's a couple of little nuances here. So the first thing is that a VNA generally can measure a fairly large dynamic range. I mean, it can sometimes look at, like, let's say you're designing a filter, for example, it can show you, like, if maybe you're measuring the duplexer for a repeater or something like that. You know, you're talking about being able to see, 50, 60, 70, 80, 90 dB down. Right? That's a huge dynamic range in terms of, signal levels that are being measured. The NanoVNA isn't quite that good. It's typically about 60 to 70 dB, but that's still a huge dynamic range. So any little nonlinearities and leakage paths and things like that, can affect the ability to measure signals that are so different in amplitude. So the other thing we want to do is to compensate for phase. As we talked about earlier, as you send a signal down a transmission line, the phase of that signal changes, right? Because phase is just a function of delay, and you got some propagation delay. Now, if you want to measure the phase change at your device port, okay, where you're connecting up to it, you've got a little bit of coax between the VNA itself and the device you're trying to measure. So there's a delay there. And you might want to remove that from the measurement, so the measurement you measure is only at your device. So what you're doing is you're establishing what's called a measurement plane. So you want to normalize everything at the device port, of your particular device itself. So part of the user calibration is to remove the effects of your interconnecting cables and adapters and things like that. So you're measuring the response right at your particular device of interest. So establishing that reference plane is another reason why we do this user calibration. Of course, a factory calibration can't account for all of these things because it doesn't know how you're connecting things up and where you want to establish that reference plane. And there's a number of little nonlinearities that are always going to be kind of systematic errors that you want to try and take out when you can. So this is why we run a user calibration. It really enhances essentially the instrument's regular calibration and can establish that new measurement plane at the connection point for your device. So when do we want to do a user calibration? Really, whenever there's a configuration change, meaning I'm changing my cables or adapters, I'm changing a fixture that I'm using to measure a device, or when I change and make when I'm changing the frequency range that I'm making a measurement on. Because when we run a calibration, it's measured at a specific number of points across a measurement span. If you change that frequency range, then the calibration points aren't necessarily going to be the same points that you're measuring. The VNAs will typically try to interpolate the results between those points, but it's always best to recalibrate. It only takes a minute, okay, to recalibrate whenever you make a frequency range change, okay? So before I move on here, does anybody have any questions? Clear anything up before we move on?
I have a quick question.
Sure.
What frequency range change would require recalibration?
That's a good question. It depends. Let's say I calibrated my unit from, say 14 megahertz to 14.3. Okay. And I maybe shifted my measurement range to be 14.05 to 14.2 or something like that. That's probably close enough that as long as your VNA interpolates, between calibration points, you're probably okay. But if I set up and made a measurement range over, say, the 40 meter band, and then I changed to, say, the 15 meter band, I'd probably want to recalibrate. Okay. But some VNAs do not do an interpolation when you change ranges. So as soon as you change the measurement points, you got to calibrate anyway. So it really depends on the VNA, but most will do interpolation between the points.
Thank you.
Okay, sure.
Question and 5JEF.
Sure, go ahead, Jeff.
I wonder if you could say a little bit about the dynamic range. You said about 60 dB dynamic range with a Nano VNA,
Yeah.
as opposed to a maybe more like closer to 90, 100 dB, I suppose, with a professional quality VNA. What are the consequences of that difference?
That's a good question. And where that comes into play mostly is when you're looking at filters, okay? Because especially if you're looking like, say, a duplexer for a repeater, for example. You typically, for a repeater, you might want 90, 100, 110 dB of isolation between your transmit frequency and your receive frequency to avoid any kind of problems. And if you're using a VNA to sweep that filter response, if the VNA can only show you 60 dB down, right, you'll see the passband, no problem, close to 0 dB of attenuation in the passband, but then the band that you're trying to reject, maybe if you want to try to adjust for 100 dB down and the VNA can only show you 60 dB down, you really can't tell when you're really optimized where that filter is. Make sense?
Understood. Thanks for that clarity.
Sure, sure. So just following up on the user cal, it really corrects for, again, what we call systematic error sources. And these are things that are kind of predictable in a sense that they're controllable. They're not kind of random. And they're things like what are called tracking errors. And this is really the source and receiver frequency response for the RF source and the measurement receivers themselves. So part of the user cal takes out or normalizes out the frequency response of these devices. Also, what's called a source and load mismatch. So, you'd ideally have a 50 ohm output impedance, 50 ohm input impedance of these ports, but if they're not exactly that, you're going to have some reflections at those ports, even not including the DUT. And the user cal can take care and accommodate or account for that, so it doesn't become part of the measurement of your DUT. And then also directivity and leakage. Directivity is the measure of how well these little directional couplers measure the intended signal direction versus measuring the unintended signal direction. So whereas like this directional coupler ideally would only couple some of the energy going this direction and none coming back. But the reality is there's always a little bit that gets reflected from or injected from the other direction. That's called directivity. We can measure it and account for it. Or crosstalk. So for example, if there's any path for any signal to go from port 1 to port 2 bypassing your DUT, you want to be able to account for that as well. Okay, so these are all things that the user calibration will kind of try to measure and take out of the measurement to give you the best results. And then finally, any user cables and fixtures to establish that reference plane right at your DUT connections. Okay, so that's what we're doing with that user calibration. So what are some of the common display formats for a VNA? Now, again, most measurements on a VNA are made versus frequency. So we're measuring things like reflection coefficient or S11, okay? And this is the signal being reflected off that port. Oftentimes that's going to be shown to you in a log magnitude response, where 0 dB means that essentially all of the energy is being reflected back. A minus 20 dB S11 means I've got a pretty good match. My signal being reflected back is 1/100th of what I applied to it. Okay, so the log magnitude is typically the format that you'd use to look at the reflection coefficient. You could also do some math, and instead of plotting reflection coefficient versus frequency, you can plot SWR versus frequency, and that's typically shown in your traditional, linear ratio. 1.2 to 1, 1.5 to 1, etc. So you'll have a linear ratio versus frequency. When you're looking at a complex impedance, like the impedance looking into a device port, that's often plotted on a Smith chart. It's a topic for a whole another presentation, which we can certainly do at some point. I've got a presentation, a talk I've given on Smith charts, so that's something we could talk about if there's ever an interest on that. But typically the complex impedance versus frequency is often plotted on a Smith chart. Transmission coefficient, again, this is the through characteristics of the device, whether it's coax loss or the characteristics through a filter or something like that. And similar to S11, that S21 is often shown to you and plotted to you as a log magnitude versus frequency. So again, 0 dB of S21 means that I've got a nice lossless connection between those two ports of my device. So it's a good way to look at maybe loss of your coax over, over a frequency range, or if you've designed a filter for an application to see how well that filter is behaving and that type of thing. Insertion delay, insertion phase, group delay, these are typically all linear in degrees versus frequency. Or the group delay is actually a function of its time, but it's still showing essentially phase versus time in its sense. Now I kind of hinted at earlier that there's some additional processing called a time domain transform, where measurements are made versus time. And this is where you might be measuring the length of coax or the distance down coax to a fault, like an open or a short. And typically it's helpful to, in what it's going to plot essentially is the reflection coefficient versus essentially distance, okay, or time. It's often helpful to change it from log magnitude to linear because we get a sharper response. It'll be easier to kind of figure out where that specifically where a particular discontinuity is. But these are the common display formats that you can, and there's many others you can choose from, but these are the ones that you'd use most often with depending on what you're trying to measure. So let's focus a bit on the Nano VNA, what it is, how to use it, okay? So the Nano VNA actually started off several years ago as kind of a project that was put in the public domain by a couple of different folks, and it had been picked up by several, kind of developers, mostly over in China and things like that. So there's a couple of different variants that are out there. The original, often known as the H version, okay, was just a little 2.8-inch display. It didn't even have a case like this one has. It just had like a couple of boards and a display kind of bolted together with the connector sticking out one side, and didn't even have a battery. And that was kind of the original device. After a while, some folks started selling them with a little molded case and things like that. The real problem is that the display was only this little 2.8-inch display. And for anybody older than 23, you couldn't see it. So we started to see some other variants come out with a 4-inch display. One of the units that I have here is the NanoVNA H4. That's this one pictured right here. And it's got a nice 4-inch display, a nice molded case, and it's a nice little unit. It's got a built-in battery, the whole thing. That's actually the one that I use most often. Some other developers said, hey, there's probably other ways to skin the cat here. So there's another developer who kind of went his own direction, and this is the NanoVNA-F. Also a 4-inch display, a little bit different operating system. The firmware is a little bit different. He's actually did some things that I actually like a little better. It's a metal case, like an aluminum case instead of a plastic case. It's a little more expensive. It's about $120, but I think it's got some nice little features there. One of the things that he did that I like is that he properly called these ports, port 1 and port 2. For some reason, the NanoVNA calls it channel 0 and channel 1. Channel 0 is port 1, channel 1 is port 2. Okay, so like the names S21 and S11 don't really make sense with this channel nomenclature. So if you get this, just get your label maker out and call this port 1 and port 2. You'll be good to go. Okay. Some of these developers also kind of went off and said, we can do even better. This approach that they use in the Nano VNA is good, but we're going to do a new one. And they gave it this really unfortunate name, SAA2. It's also called the V2, a little bit higher frequency range. Initially kind of came out in this kind of stacked form, again, without any case. Now we're starting to see some now that are coming out in cases and things like that. A little bit higher frequency range, and they're pretty decent devices as well. So as of, about the fall of 2020, I still kind of like the H4. The reason is it's been out a little while. It's kind of stable. There's not too many people that are doing other variants of it now. There's a pretty broad range of support that's out there. Other people that are developing firmware with some really nice features, and we're going to talk about here in a minute. And they're easy to get, about $60. Really kind of hard to beat. So I kind of like the H4. This SAA2 or the Nano VNA-V2 is kind of the name for it. A little better performance than the H4. Again, initially came out as a 2.8-inch display. We're starting to see a couple of people, different variants coming out with 4-inch displays with end connectors and things like that. The problem is that because none of the nano VNAs are made by like an MFJ or a rig expert or somebody like Array Solutions or something, it's all being done by these just developers that are getting stuff built in China and things like that. There's no standardization on this, so that's kind of why I say, well, let's kind of go with things that are a little bit more stable. Right now, the SAA2 thing, there is kind of an official site that I'll show you here a little bit later, where you might want to go where where the core developers are still kind of doing their improvements and things like that. So I'd probably still hold off a little bit before pulling the trigger on one of these guys, simply because they're making some changes. But again, it's a moving target with these things because it's kind of an open source project. So again, the SAA2 guys are developing some improved units. The most recent one is called the V2+4. It's got a 4-inch display, goes up to like 4.2 gigahertz, got some pretty decent dynamic range. So again, they're always making some improvements on this. So you kind of have to go check the websites out to see what's out there. So a couple more details. All of them are 2-port, 1-path. And this is where I mentioned where they've got 2 ports. One port, it provides the source signal and can measure reflections on that same port, and then a second port to measure the through parameter. So that's the 2-port, 1-path. The H4 that I'm talking about goes from about 50 kilohertz up to 1.5 gigahertz in terms of measurement frequency range. It offers standalone operations, got a built-in battery. The battery lasts a couple hours, so it's kind of handy. Okay. There's also a PC application available. One of the more popular ones is called NanoVNA Saver. And you plug in the NanoVNA. With the saver, you can separate all the plots out instead of having them all overlaid. You can change the number of points and do a couple of other nice things with that. But to me, it takes away from the portability aspect of it, because you got to be tethered to the computer with a USB cable. So probably the more common website is for all of the H and H4, all the original versions, is just nanovna.com. That's kind of your launching point. And that's going to give you kind of just a real basic menu to get to places. This wiki and user group, that's this website right here, is kind of where you can sign up in the mailing list, and there's all kinds of files that are available. There's help files, there's links to firmware, all kinds of things like that you can find at this site here. Again, there are 2 separate groups for the SAA2, that kind of separate version, but kind of the official website for the guys that are actually doing the hardware development on the SAA2 is this one here, nanorfe.com, and there's NanoVNA-V2. So, and there's, again, good information there if you're interested in kind of looking at that route. Okay. So underneath the hood of the kind of the H and the H4 nano VNAs, it's a pretty simple device. There's essentially, here's our channel 0 and channel 1, or again, port 1 and port 2. All right. Here is the RF source. Okay, it's a chip that is just a programmable synthesizer. Okay, that is being controlled by a microcontroller. This bridge right here is taking the place of those directional couplers that I showed on the block diagram. And then we essentially have all of these 3 mixers, our familiar SA612 or like a NE602 type of a mixer, that's used to take the signal and mix it down to relatively low level or low frequency signals that are then sampled and characterized in this low cost stereo audio codec. This is like a sub $1 audio ADC that's used in a lot of audio equipment, but it's so high volume that it's dirt cheap. So it was easy to incorporate into this design to use as a receiver by taking these RF signals, mixing them down to audio, and then sampling the audio signals, and then doing all of the processing inside this microcontroller. So the microcontroller controls the synthesizer to create the RF signal that we're testing, and to control the local oscillators into the mixers, so that we can convert those signals to a low frequency to be measured in the stereo codec. Okay. So this is actually the schematic. I'm not going to go through it in detail, just kind of point out where all the various bits and pieces are. Okay. So again, the RF source right here, the channel 0 or the port 1 bridge right there, the receive pad here for port 2, which is channel 1. There's our mixers right here, the audio codec, whoops, go back, the microcontroller up here, and then interface out to the display over here. So, and then all of the other, USB, battery charger, voltage regulator. But it's, again, it's a pretty simple device. Again, that for 50 or 60 bucks, it's not going to be very complex. So let's take a look at the user interface for the Nano VNA. So on the device itself, there's a little jog wheel that you can rock back and forth to move things, move markers, make selections in menus, and you can push it down to select things. So it's a kind of a rock back and forth and push type of thing. It is a touch screen, so you can tap to select things. You can tap and slide to like move markers and things like that. And it also has a fairly simple menu structure. Okay, the home menu kind of starts off with this thing for the display menu leads you to selections for the traces and the channels and format. The marker menu allows you to add and remove markers and do searches on the markers. The stimulus allows you to set start and stop frequency and span, etc. Okay. You also can save calibrations into various measurement slots. So if you did a calibration, there's something like I got 3 antennas and you want to measure, I always measure those antennas at the same frequency range. You can just run the calibration, save it into the various slots, one for each antenna, for example, and then never have to run the calibration again. Just recall the memory slot for that particular cal. There's a USB port down on the bottom that allows for charging of the battery as well as the PC interface. So let's walk through kind of how we use the menus to do the calibration. Now, something to think about is that most of the VNAs, the Nano VNAs, measure over a frequency range, but just using 101 points on the sweep. Now, I put an asterisk here because there are later versions of firmware that on some of the units will actually go higher than 101 points. But you have to think about that because if you do a wide range calibration, the spacing between the measurement points and therefore the calibration points is going to be fairly big, right? If I did a measurement or a calibration from 1 meg to 30 meg, so I got a 30 megahertz span, I'm only going to have I'm going to divide 30 megahertz by 100, right? I'll have a 300 kilohertz spacing between my calibration points. Well, some of the HF bands aren't even 300 kilohertz wide, right? So you won't even have a calibration point inside a particular band of interest, right? So, but again, with some versions of firmware, you can go up as high as 401 points, or the external PC application allows you to have more points as well. And as I mentioned, most will, after you run a calibration, will actually interpolate values between those measurement points. So you can still get reasonably close, but it's a good idea to try to calibrate over the particular frequency range you want to measure. So that's always a good idea. Okay. Again, note that some firmware from other developers, there's a developer out there called Dislord that have increased the number of measurement points up to as high as I've seen 401 points on the unit itself. And that's the firmware that I'm running on mine. So that is a little bit handier. So on the unit itself, the calibration indications are way over on the left-hand border of the display. The capital C is indicating that over the frequency range that you're looking at, we are currently calibrated. If that letter C is a small c instead of a capital C, it means that you've got a calibration loaded, but it doesn't match the measurement frequency range that you have set up. So you're doing interpolation. And then the number that follows that indicates which memory location the current calibration is being used. So if I've stored a calibration in slot number 2, and I recalled that, this would say a 2 here, okay? The D, R, and S mean that the directivity, reflection, and source match error corrections have been applied. These are all applied on channel 0 as part of the calibration process. So that tells you that you've properly calibrated out those systematic errors. And then the transmission and crosstalk corrections have been applied, and would be the 2-port measurements for transmission. So the transmission tracking error and the crosstalk, right? This first set is needed generally for all measurements, SWR measurements, return loss measurements, things like that. This last set is really only needed when you're making transmission measurements through a device, like through a filter or something like that. So you don't really have to do a portion of the calibration if you're only going to be using this to measure reflection properties like sweeping an antenna, for example. So here's how you actually do the calibration. All right, that's just a good walkthrough for the menu process as well. So just tapping on the display or pushing down on the rocker, you'll come up with the menu. And then from there, if we hit cal or calibrate, depending on the version of the menu, it'll say one or the other. That brings up the calibrate menu. And then from there, you can hit reset to reset the existing calibration, and then go and hit calibrate. And once you do that, it's going to prompt you with this menu structure for open, short, load, isolation, and through. And what this is prompting you to do is to apply an open circuit to channel 0, and then apply a short to channel 0, and then apply a load to channel 0. And what these do is provide a reference that the VNA uses to say, okay, and now I know what an open, short, and load look like after all of my connections. Okay, so I can calibrate out any of these other errors and the interconnection to my device under test. Okay, and again, required for all measurements. The isolation and through measurements are to essentially measure crosstalk and the tracking errors and things like that, and for the second port. These are only required if you're making S21 or through measurements. Once you've kind of gone through each of those, and literally I said it takes less than a minute when you run it. You hit done, and then it'll come up with a menu to ask you what slot you want to save that calibration into, and just tell it a number. Anything you save in slot 0 on most of the VNAs is recalled upon power up. So if there's something you do all the time, just save it to slot 0. So every time you power it up, it's going to be ready to go to make that measurement again. Okay. And ideally, you want to connect all of these calibration standards to the same place where your device would connect. Okay, so that establishes that measurement plane right at your device.
Quick question, if I may.
Sure, go ahead.
If you back that one slide.
Yeah.
When you hit the calibrate, you're saying do a reset versus hit the calibrate at the top.
Yeah, reset just kind of clears everything out. It probably isn't absolutely necessary since you're running the calibrate. It's just kind of force of habit I like to start from a clean slate. Because if the previous calibration was kind of way off when it goes to make the measurement, it might you run into some screwy situations. So just a good idea to reset it to start.
Versus hitting the calibrate on the middle screen.
Yeah, rather than going right to here and hitting calibrate, just hit reset once and then go to calibrate. When you hit reset, you'll see those indicators from that are on the left side disappear. And then you know you're starting clean, and then hit calibrate.
Thank you.
Okay.
Hey, Alan, a quick question here. If
Sure.
I'm calibrating, do I put these little things on the pigtail that's already attached?
Well, it really depends on how you're connecting to your device. So if you're measuring an antenna, for example, and you're going to connect that right to the input, then you can right to the connector on the VNA, you can connect these right there. If you're connecting through a pigtail or something like that, that's not going to be the same place where you're actually using it. That ideally you'd apply those, as close as possible to your whatever device, wherever you want to make those measurements. In some cases, it doesn't really matter, right? So it all depends on, for example, if I'm just characterizing my antenna, and I'm going to use the VNA to tune an antenna tuner, for example, or a transmatch, till I get the lowest SWR, then it almost doesn't really matter, because once the tuner has corrected the impedance mismatch, no matter the length of coax on the transmit side of the tuner, it doesn't really matter. So in that sense, it doesn't really matter if you connect these devices right to the VNA or at the end of the pigtail. But if you were characterizing, say, a filter that you were putting inside of a homebrew transceiver, for example, then you want to ensure that you do the calibration at the input, essentially where the input of your filter would be connected. Okay, so you account for the phase of that pigtail. That makes sense?
Great, thank you so much.
Sure. Okay, so this kind of just talks a little bit more about that because sometimes it's not practical to do that, right? Ideally, this is how I'm going to measure my device. Say this is a filter that I homebrewed that I'm going to stick inside of a receiver I'm building. Ideally, what I want to do is take that connection and basically that's where I want to connect, those calibration standards so that I'm establishing that measurement plane right at my device connections. Sometimes that's not possible, right? Because ideally, this just removes the phase of the connections and things like that. Sometimes that's not possible. The connections are different or something like that. Maybe I'm soldering something down to a board. So sometimes it's not possible. But so what you can use something that's called port extensions to move the measurement plane. So let's say, for example, I made the calibration at this point, but in order to connect to my DUT, I've soldered on a coaxial pigtail to my device. Okay, and I can't really connect the SMA standard here, so I'm going to do it here. But as long as the extension that you've got to get to your device is that same impedance, that same 50 ohm coax, you can mathematically just subtract that out by using something called a port extension. Okay, so what that does is it just says, okay, I know that I'm adding this much more length before I get to my device. Okay, the Nano VNA calls this electrical delay, and you can adjust this. You can actually test and make adjustments of this, usually with some simple fixturing and things like that, to remove the phase of that interconnect. Sometimes just having that open as an interconnect, you can look at it. And this is where the Smith chart can actually be handy. Because on the Smith chart, the 3 o'clock position represents an open circuit, a perfect open circuit. The 9 o'clock position, over on the other side, not shown here, represents a perfect short. If you have a delay, okay, out to that open or short, you're going to rotate around the Smith chart. So by dialing in the port extension length and dial it in until you get back to that open or short at your DUT, you're essentially dialing out the delay associated with that interconnect. Okay, I got a video on this that you can go through a little more detail, but I just wanted to explain what that was. And again, it's really only important when you must have an accurate phase measurement at your DUT. Okay, and this again may be only important oftentimes for component level types of measurements, as opposed to maybe making it a measurement on an antenna you're connecting up to your transceiver. It may not matter so much. Okay. So let's talk a little bit about the Nano VNA channels and traces, right? Channels, as we know in the VNA, is channel 1 and channel 2. The channel 1 is essentially the reflection channel. This is the one where the source is going to, the source signal is being applied, coming out of channel 0, and then we're measuring signals being reflected back into it. So this is kind of like your antenna analyzer port. It's to measure S11 or the reflection coefficient, to measure SWR, to characterize things like input impedance of a device, to do distance to fault. That's all done using channel 0, and what on a traditional VNA would be called port 1. Okay, so display, and then under channel, so this is where I might select a particular trace and tell the trace to be on channel 1 or channel 2. So the traces, okay, so under the display menu, you go to trace, say, okay, I want trace 0 to be on channel 0. So trace 0 then will be one of the 4 traces that it can have on the instrument. I want that trace to be on channel 0. Maybe I want trace 1 to be on channel 1. So you can decide what, you can do measurements up to 4 traces at any time. That can be any combination of channel 1 and channel 0, and any combination of different measurement formats. Okay. So you can essentially assign any of those 4 traces to any channel, or you can just turn them off. If you just want to turn off all the traces, have one trace that shows SWR versus frequency, very simple. You can go do that. And it makes it very simple to look at. It looks like any other antenna analyzer, for example. So common trace formats, these are through display, trace, and then format. Are for channel 0, again, you're making those reflection measurements. The most common thing is to look at the log magnitude of S11, or maybe use the Smith chart if you're measuring complex impedance, or look at the SWR. Those are the more common ones for channel 0 measurements. For channel 1 measurements, these are your transmission measurements. Like typically, again, the log magnitude or loss and gain, again, the S21, or maybe the phase or delay of a device under test. So these are the most common formats for these different types of measurements. There's a lot of others you can select, but again, these are the ones you want to worry about most often. Again, there's more, but again, it depends. If you're really getting in depth with RF design and things like that, you might start using some of these others. But for most of us as hams, we'll be looking at log magnitude of transmission properties or log mag of S11 or Smith chart or SWR using channel 0. Setting the source or the stimulus. This is to set the frequency range that we want to make measurements over. Okay, you go down to stimulus, and you can either pick whichever is easier by setting the start and stop frequency. Sometimes that's easier if we want to measure over a particular frequency band, okay, 14 megahertz to 14.3, for example. Or sometimes maybe if you're measuring like a bandpass filter, it might be easier to set the center frequency and then the frequency span around that center frequency. So you can choose any combination of these to make a measurement, but it's usually picking, setting the start and stop or setting the center frequency and span. Anytime you select any of those, a numeric keypad pops up to allow you to select that. The CW frequency allows you to set up to do single frequency analysis. I'll often do this when I want to tune up my transmatch. Okay, I'll set it to a particular frequency, like 7.05 megahertz. Stick that, connect that up to the input of my transmatch, adjust the transmatch to minimize SWR. Maybe I'll minimize the input impedance by looking at minimize the reflection by looking at the Smith chart or something like that, tune my antenna tuner, and then I'm good to go. All right. So then there's markers that you can use to help you make some measurements. So here there's a couple of different traces turned on here. When you put on a marker, it shows up on every trace. The way you look at this is that the marker values is typically shown kind of as the second number on each on the trace legend here. So the markers, like in this case for channel 0, which is the yellow trace, this is the log magnitude. In this case, since it's channel 0, that's the log magnitude of S11. Okay, it's essentially the reflection coefficient. Okay, and that's at 10 dB per, means that this is 10 dB per division. All right, and then this is the value of the current marker. In this case, the current marker is marker number 2. Okay, that's the selected marker, and its value at that frequency, which is shown right here, 360 megahertz, is minus 8.19 dB. With a lot of these devices, you can put up a second marker, and once you do, you essentially get a delta. And what the delta shows is what's the difference from the previous marker that was active. In this case, the previous marker was 1. So there's my 1 marker down here. So this D1, what that does is this is showing me the delta, in this case, the delta in frequency between those two markers. Okay, all the markers track each other on all the different traces in terms of, they'll all be at the same frequency. So the channel 1 marker is at the same frequency on all the traces that are active. The search features allow you to search for min and max, or just search left and right for the next peak, that type of thing. And you could also do some operations. What the operations do is say, let's say I move this marker to here. Maybe this was the peak of my filter. If you do it, you can do a marker to center, for example. And what that will do is change the center frequency to wherever the marker is. So it's a simple way to say, I found my peak right here. Let me make the center frequency of the analyzer right there. Okay. And then you could also set the Smith chart units. So again, for looking at complex impedance, you can set it to show things like resistance and capacitance and inductance, or have it show complex magnitude and phase or something like that. Okay. So here's the basic setup process to actually use the Nano VNA. Okay. You set up and configure what traces you want on, like how many traces do I want to look at? Maybe I just want to look at SWR. Okay. Or maybe I just want to look at my S21 parameters or whatever it might be. So tell it how many traces you want on, what channels those traces are on. The channel determines whether you're making a reflection measurement or a transmission measurement for that trace, and then what format those traces are. And then you set up the stimulus frequency range. Now, those two things can be interchanged. You can start off by setting the stimulus and then set and configure the traces and channels. Okay, but usually those are the two first steps that you do. The third step is to run that calibration. Okay, now that I've established the stimulus, I want to run a calibration and then save it. So that now I've got it, and I can go back and return and make the measurements. After that, I connect my device and I go and make my measurements. extract what I want to go look at, do what I'm doing with it, and then I'm essentially done. I can add markers, make some extract some numbers off, things like that. And then if you want to adjust the traces and formats, you can add traces, take them away, things like that. That's all fine. If you go and change the frequency that you're measuring, then you probably want to recalibrate again. Okay, but just changing which traces are turned on or off and what channels they're on, you don't have to rerun a calibration, only really if you change the stimulus or the frequency range. So here's an example of measuring an antenna, for example. So I've got an antenna, right? This really sophisticated antenna connected here to channel 0 or port 1. Okay, and down here along the bottom, this is the frequency range that we're measuring over. In this case, I can see I set a start and stop frequency, 7 to 7.3 megahertz. So this was measuring my dipole antenna here. I had the tuner set up for the phone portion of the 40 meter band. This plot here, okay, so let's look at this. So this plot here, this blue trace is SWR. So we can see here it's channel 0. It's showing SWR 1 per, meaning that this is 1 to 1, 2 to 1, 3 to 1, 4 to 1. Okay. This marker, which I unfortunately didn't move, the marker is sitting way over here. Okay, you can see it's sitting at 7 megahertz, and that marker is showing an SWR of 4.73 to 1 down at the very bottom of the CW portion of the band. Okay, you can see it going all the way down to essentially near 1 to 1 way up here. Okay, the green trace here is on channel 0, so it's a reflection measurement. It's on the Smith chart, so it's essentially showing me complex impedance. And we can see that where this marker is, this is 16 ohms at 822 nanohenries. And as we walk our way through right at this point in the center, and it's kind of hard to tell that, but right where I'm pointing here in the center is essentially this frequency here where we've minimized SWR and got the lowest possible best reflection loss or return loss. So this is the reflection coefficient. Okay. Again, reflection coefficient and SWR are mathematically related to each other, so they're both going to give you the dip at the same point. It's often easier to see the location of that dip on a log magnitude reflection coefficient plot as opposed to SWR. It's very easy to kind of see where that point is. It's kind of a little bit shallower on the SWR plot. Okay, and we can tell that is a reflection coefficient because it's on channel 0 and looking at log mag. All right. So let's look at another example measuring a filter. This is actually measuring a low pass filter that I designed for the output of a little Michigan Mighty Mite 75 or 80 meter CW transmitter that I built. And so again, the frequency range down here at the bottom from 1 megahertz to 15 megahertz. The insertion loss, okay, if we look at this blue trace, okay, see that's channel 1 log mag. So channel 1 means that it's my S21 measurement, okay, and the log magnitude of that. So I'm sitting up near 0 dB. This is my pass band, all right. And then at 10 dB per division, I'm 10 dB down, say here, 20 dB down here, 30 dB down here as I walk my way down. I can see marker 1 is sitting way down here at about 10.5 megahertz, about the third harmonic of this 3.58 megahertz transmitter. So I can see my third harmonic is 47 dB down, okay. The SWR looking into the filter is shown here in the purple trace. Again, channel 0, SWR. I can see it's all down below 2 to 1 until I start rolling the filter off, and then the SWR rockets up, which means that the signal is being reflected off of the input of the filter, you know, by second, third, fourth, fifth harmonic, etc. Okay, is not getting through the filter. See the reflection coefficient. This is another way of looking at the input return loss. I can see that I'm better than 10 dB down, over the pass band of the filter, and then the reflection coefficient gets close to 0 dB, meaning I'm reflecting all the energy off the input of the filter when we get up in these higher frequencies. Okay. So then the input impedance, which I really didn't have to plot here, because I left it on just kind of this little curly Q on the circular Smith chart axis here. So let's say I want to measure the length of coax. In this case, we're using the time transform capability of the analyzer, and I'm using channel 0, and I set it to linear instead of log magnitude. So this gives me a linear measurement of the S11, but in this case, because of the time transform, the x-axis is now time, okay? So it tells me how long it takes for that reflection to come back from the end of the cable or a discontinuity in the cable or something like that. And if you tell the analyzer what the velocity factor is of your coax, when you put a marker on there, I'll actually tell you the distance. So this was 9.13 meters. So it was like a 21, 22, 23 foot piece of coax that I was measuring here. So that actually showed me, right where that length was. So it measures time in this axis, but then converts that to distance as long as it knows the velocity factor. Now, of course, if we change modes and turn the transform off, we can measure, something like, insertion loss of that coax by connecting it up to the other end and measure insertion loss versus frequency. So as with anything, there's the good, the bad, and the ugly of the Nano VNA. Okay, so there's some limitations and downsides, right? This thing only costs $60, so it can't be perfect. So there are going to be some limitations. Let's take a look at that. Again, most cases, 101 trace points. So external software like the Nano VNA saver I mentioned can help with that. But otherwise, you've got a pretty granular measurement range. So you want to kind of focus your measurement ranges to be over the specific frequency range of interest to get good resolution. Okay. You don't want to calibrate over the whole HF band and then make measurements just on 17 meters because you're not going to have enough resolution to see that. So if you're looking even like at a multi-band antenna, you probably want to sweep one band at a time as opposed to sweeping all of the bands. Again, third-party software helps that. Now the output of this, of the Nano VNA, is not a sine wave, right? It's a square wave, all right? And so this is actually what it looks like on a scope. Okay, there's a square wave. Okay, and on the H4, for example, it uses the fundamental, and this is the square wave in the time domain, and this is what that signal looks like in the frequency domain up here. This is the spectrum plot of it. So my fundamental, third harmonic, and fifth harmonic. So on the Nano VNA H and H4, the measuring signals up to 300 megahertz uses the fundamental of the square wave. But when you make measurements from 300 meg to 900 meg, it uses the third harmonic of this square wave. And from 900 meg to 1.5 gig, it uses the fifth harmonic of the square wave. Okay. So this output that I'm showing you right here is a 200 megahertz square wave. It's the same exact signal that's used to measure at 600 meg and at 1 gig, right? Because that's the third harmonic and the fifth harmonic of that square wave. So it's not a pure RF signal generator, okay? It's a square wave generator that's got all this harmonic energy. So you've got to consider whether the device you're measuring is going to have a problem with that, okay? If you're measuring a broadband RF amplifier, for example, you've got to think about the fact that you're supplying it with a signal that is rich in harmonics, and it's not just a pure RF signal. And is that going to pose a problem? Okay. The other problem compared to a true VNA is that the output power is not adjustable. Okay, it's a square wave of essentially a constant amplitude. Okay, and on the H4, that's what I made the measurements on. The fundamental from 50K to 300 meg, it's this 600 millivolt peak to peak square wave that gives you somewhere between 0 and plus 2 dBm, so about a milliwatt to a little over a milliwatt, or close to 2 milliwatts of power at the fundamental, and then a good 10 dB lower than that at the third harmonic, and another approximately 10 dB lower than that again on the fifth harmonic. You can't adjust it. Okay. So again, is this the correct power level for the device you're measuring? If you're measuring something like an antenna or a passive filter or something like that, it doesn't really matter. But again, if you're measuring an active device, like an active filter, or an amplifier or something like that, you've got to start considering, do I have enough signal there to drive that device, or am I driving it too hard? Am I going to drive it into compression or create distortion on my device because of that signal? And is the fact that it's a square wave going to be an issue? So these are things you might want to think about if you're going beyond just measuring like a passive device. Okay.
Alan, question.
Yes, sir.
Yeah, it's Gordon.
Hey, Gordon.
WTTT. quick question. If I'm a lucky guy who's got an SAA2,
Yeah.
and so I'm thinking that it's probably the 7th harmonic, and again with scaled output, reductions, or
Yep.
do they buffer it? Do you happen to know by any chance?
Well, actually, the SAA2 uses a different synthesizer, and
Okay.
it's still a square wave output in most cases, but it uses a fundamental for all the measurements.
Oh, really?
Yes, at least for the SAA. I've got an SAA2N, and that one I made a measurement on, and it uses the fundamental all the way up.
Okay. Yeah,
Okay.
I like mine, but the only question is I'd love to see an SAA2N with a 4-inch display.
Yeah, well, that's what I have. It's not
Okay.
it's not officially sanctioned by the original developers, so when buying it is not supporting the original developers. I learned later, but I do have, that's the one I have is the SAA-2N, and it actually does have a 4-inch display.
Okay.
So, and then those guys are working on a couple of other variants of it now, which is probably worth waiting for to go up a little north of 4 gigahertz. So
Good. Thank you,
okay.
sir.
Sure. Again, we talked a little bit earlier about the limited dynamic range at the first harmonic or the fundamental. You're probably talking in the neighborhood of 60 dB. You get up to the highest frequency range, you may be down as low as 40 dB or a little bit less. Some of the newer vert models that we talked about, like the one that Gordon mentioned, the SAA2, they're better in terms of dynamic range, but they're still not going to come close to what some of the professional units get. But again, for $50 to $100, you're getting what you pay, getting a lot more than what you pay for still. The measurement resolution bandwidth is not adjustable in most cases. Some third-party firmware that's out there, some other developers have developed some firmware where you can adjust the resolution bandwidth. But again, it's of somewhat limited utility because of the limited number of measurement points that you have. And of course, there may be some other limitations as well. So, there is some good, bad, and ugly with the NanoVNAs just by their nature. But again, for the money, it's just pretty incredible. So, kind of in summary, I would say that the NanoVNA is probably the RF tool or toy of the year in terms of bang for the buck type of capability. If you're considering an antenna analyzer, the NanoVNA is a nice choice. The downside is that it's not going to be as rugged as like a rig expert or something like that, and the display isn't going to work as well in bright sunlight as some of the other things. But these are trade-offs you might be willing to live with for $60. Okay, so really amazing capability for that $50 $60. There's a ton of videos and things like that are out there to learn how to use it, because there isn't really even a good user manual that's out there. Some very active user groups online to kind of learn more about it and get problem solved and questions answered. And what I found in the US anyway, because of all the various clones that are out there and things like that, you don't know where to buy it from and who to get it from or whatever. Go to a kind of a more reputable dealer. And the guys at R&L Electronics generally are sourcing them from good places. And I've purchased 2 devices through them, and they've both been built well, and they look like they're of good build quality and that type of thing. So they're good to deal with.